All right, so today we are going to be chatting evens, which evens and odds. You're going to be doing evens. I'm going to be doing odds. So that's an even. So let's flip over here. We'll start pretty straightforward, and then we'll start adding some twists and turns as we go along here. So we're actually over on 3B, and we're going to start at 13 here. So Bill's an architect, making a new parking garage for the city. The floors of the garage are to be 10 feet apart. So again, most parking garages, level on level on level. So it's almost like, okay, so there's a floor up here, then here's a floor, so 10 feet between. That makes sense. The exit ramps between each pair of floors, as we go down to get out, are to be 75 feet long. So we got that labeled for us already. This is nice. What is the measurement of the angle of elevation of each ramp? Okay, so when we're talking about angle of elevation, I always tell people, think about it this way. If you're standing down here, hopefully not when a car is coming down, but if you're standing down here and you're looking up, you're looking at an angle that elevates up towards where that next floor is. When we get to an angle of depression problem a little later, I'll explain what the difference is, but there's a very big similarity. So, just something to be aware of. But I got everything I need here. I've got me a right triangle. I got two sides. Here's my reference angle, where the X is. We go opposite to get here. And opposite of my right angle is always the hypotenuse. So now I got to go back in the memory bank a little bit. I'm like, okay, which one of our trig functions is opposite over hypotenuse? Sine. So we're going to be doing the sine. The inverse of sine, because I'm looking for an angle, is opposite over hypotenuse. So, breaking things. Couple of reminders. When you first turn on, always make sure that you're in degree mode. If you're in radian, your answers will be significantly different. And then here, if I do second sine, there's the little -1. That's like when it's an angle, I like to put that in there, just to remind me. Then we just type in the fraction. And normally with angles, we go to the nearest whole angle. I would not tell you you were wrong if you said 7.7 degrees. That'd be fine. But yeah, normally angles, full degree, sides, normally the nearest 10th. But again, if we go a little further, that's not going to be a big deal. So sometimes it'll be nice to get a picture. Sometimes it won't be so nice. We won't get a picture. So let's move this over a little so we can see the whole problem. So at a certain time of day, the angle of elevation of the sun is 44 degrees. Okay. My right triangle here. We just got done saying, okay, angle of elevation, looking up. So I go here. Find the length of a shadow. Okay, this always tends to be one of the issues we have, and I want to kind of make sure we've got this. I'll skip to the last part and come back to this. By a building 30 meters high. Okay, so there's my building. So then the argument ensues. Well, it's a shadow. Well, where does it go? Hardy argument. It goes here. Why? Because when you're looking at your shadow, where is it? It's on the ground. It's not some like 3D hologram that's just hovering above the earth waiting for you up here. It's down here. So that's where we're going to put our shadows at. So this time, once we got our picture drawn, we have got opposite. We do not have hypotenuse. We have adjacent. What's opposite over adjacent? Tangent. So the tangent of 44 degrees, because we do have an angle measure this time, is opposite over adjacent. And if you take a moment to think back to yesterday when we were talking about how we can shortcut these, when x is in the denominator, you're going to be dividing by your trig function. If x is in the numerator, we multiply. if you're not comfortable with that whatsoever, what I just did, do the algebra. Multiply both sides by x. Okay, if you did that, grab this quick. If you multiplied both sides by x, we'd have x tangent 44 equals 30, but x wouldn't be alone. Hence, this is where this is coming from. So if you want to do the algebra that way instead, that's fine. No biggie. So 30 divided by tangent of 44, not an angle this time, so we're not gonna 31.1 meters. And again, that's reasonable. It's not like I got 2 or something. So good thing to keep track of. Now we'll start putting a couple twists in. Length and width of a rectangle are 6 and 5 centimeters respectively. What is the measure of the angle formed by a diagonal on the longer side? Like, okay, wait a minute. So, all right, so there's a right angle. So if I'm taking this triangle, but I only have one side, or do I? Do I have another side in the red triangle? Yeah, because when we're dealing with rectangles, we know the opposite sides are congruent. So I do have the 2 sides that I need. Now I'm ready to roll. So we got opposite, we got adjacent again. Tangent, here we come. Inverse of tangent, here we come. Opposite over adjacent. All right, let's see. Second tangent, 6. Pretty darn close to 40. We get that set. So you're like, okay, not terrible so far. Oh, no picture this time. All right, we'll draw. A supporting cable to the top of a 250-foot tower. All right, 250-foot tower is 300 feet long. What angle does the cable make with the ground? Okay, so here's the ground. Now, is the 300 going on the hypotenuse or the adjacent side? I agree. Because if it's a supporting cable to this tower, I hope it's going from the top of it into the ground and not along here, because I can't see how that's going to support it real well. And yes, that would make a difference. So, opposite hypotenuse, which would be sine. And so far, we have had a very strangely, very irregular amount of angles we're trying to find. It normally is not this lopsided. So second sine, 250 divided by 300. Again, if we go to the nearest, 56, 56.4 would be okay. I don't have an issue with that. Just look, like, okay. Really straightforward for the most part so far. So far. As we head to the back, now it's going to get a little more interesting. To secure a 500-meter radio tower, so, here, against high winds, guy wires are attached to a ring 5 meters from the top of the tower. Here is our first lesson with our trig pictures of things are not always drawn to scale. Like, if this whole thing is 500, but it's 5 from here to here, okay, yeah, no. But just read what it's got. The wires form a 15-degree angle with the tower, okay? Find the distance from the tower to the guy wire anchor in the ground. From the tower to the guy wire anchor in ground. So I start to look, and I'm like, okay, let's see here. First thing I'm going to do is start putting in some of the info I see already. Sometimes seeing two of them can kind of mess things up. And so I look, and I'm like, okay, so let's see, what else do we know? Find the distance from the tower to the guy wiring from the ground. Okay, so I'm looking for this. Now, here comes the question. I don't know what this is. I don't know how long the wire is. I have no idea. What's this value going to be? How far is it from here to here? Nice, okay? Because it's the whole tower minus that 5 meters lower that this ring is. So 495, well played. Now we have everything. So sometimes the info within your problem may guide you to an answer, but it may not be those exact numbers. So, opposite, adjacent, more tangent action. So the tangent of 15 degrees is opposite over adjacent. And as we saw yesterday, if x is in the numerator, we are multiplying the side times our trig function. And we're set there. So again, read carefully when we're doing this. It can pay off. Okay, a couple more little twists, but we're doing solid so far, I think here. In meteorology, the ceiling is defined as the vertical distance from the ground to the base of the clouds. Okay, so here's my clouds. Here's the ground. To measure the ceiling, a spotlight was directed vertically overhead. So, here's my right triangle. An observer made the measurements shown in the figure. How high was the ceiling? So again, if I want to draw another triangle, just so things are cleaned up a little bit, I can look at this and go, okay, well, the bottom here is 150. Got that. This is 71.5. Got that. How high was the ceiling? This is what I'm trying to find. So, I started looking, I'm like, well, okay, this isn't unusual so far. Opposite, adjacent. More tangent action going on here. Opposite over adjacent. You're like, okay, this doesn't seem like it was really that strange. Why is Hardy saying this is weird? Oh, we're about to find out. You're like, okay, so x is 448.3. But the ceiling is the vertical distance from the ground to the base of the clouds. I just did my calculation from the spotlight right here. Always watch, there may be some stuff in there that isn't mentioned in the problem but is in the picture. So here, to get all the way to the ground, I've got to add on that distance from the spotlight to the ground. Ooh. That was kind of sneaky. Now, could you put that 1.7 into your problem initially? Yes, but more times than not, it tends to be a problem doing that, and it usually just ends up being easier if you notice it to add it in at the end so you don't have problems in your calculations. So again, just keep an eye out. One last weird. Then I will step aside unless somebody's got one they want me to try out here. Okay, 27, my volleyball people. A volleyball player spikes the ball from a height of 2.44 meters. All right, so here's our ball way up here, 2.44 meters. Okay, I made it look like a basketball. Well, so assume the path of the ball is a straight line. Now we know a straight line doesn't mean straight down. It's coming at an angle. To the nearest degree, what is the maximum angle at which the ball can be hit and land within the court if the end of the court is 9.4 meters away? Okay. So now, new question. Got to figure out where the x goes. Where's this angle? Because my ball is way up here, so my initial thought might be that x should be up here where the ball is, which is reasonable, okay? This is going to be a little vocabulary here. An angle of depression. Because again, we're thinking of it from where the ball is at, but here comes the weird part. So my floor is down here. The plane that my ball is at currently is parallel to it. So we're about to ready to have a flashback to geometry here. When you have two parallel lines, okay, the actual angle would not be inside your triangle. It would be outside as it's coming down over here. But that x doesn't help me because it's not inside the triangle. So, there is this thing called alternate interior angles, which basically just forms this really big Z shape, and alternate interior angles are congruent. That x helps me. It's inside the triangle. So here's the weird connection we can make that'll make these easier. Whenever you see, and make sure I'm in the screen here, angle of elevation or angle of depression, the angle that you are going to use in your problems is in exactly the same place. So as soon as you hear angle of, that's where your angle is going to go, because by definition, they're going to end up in the same spot anyway. Weird, 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 but true. So let's actually solve this now and see how much of an angle we can rock this out at. So opposite and adjacent, and lots of tangent today. So we're looking for the angle. We won't forget our inverse. Let's see here, second tangent, 2.44 divided by 9.4. Oops, not plus. Bang. Nearest whole degree, 15 degrees, so I got a lot of room to work with. I don't have to go straight down by any means. Should be able to put this one down. So, again, your job to play with evens. Make sure you're playing with angles, playing with sides, playing with things where pictures aren't drawn, where you're having to draw them, because you'll have to be able to do this as we move along. But as always,
what does angle of elevation, like, what do you mean by
So basically what I'm thinking of here is when I have an angle of elevation. So maybe somebody says, hey, Hardy is standing down here on the ground and he's looking up at an airplane in the sky that's over here. Yep, Hardy, great drawing. No. But I'm looking up at that. So as I'm looking up at an angle of elevation. Whereas if we were saying, hey, Hardy's worried that plane is going to come down and crash on him, the angle at which that plane would be coming down towards me technically is out here, and when it's coming down. This would be an angle of depression, because if you kind of think about it, elevate, you're kind of putting your head up, depressed, you're kind of down and out, and you're naturally looking down. But because of alternate interior angles, those are one and the same. So that's why I always say, when you see either of those words, you just know that's where the angle is that you're going to be looking for. Good question. And for future people for years on as well. Any other issues before I let you have at it here? All right.